before I forget to record. So I guess right now we are almost in a stable size. So for the people in the section B, we are still be around 10, 15 seats available. So if they are interested to attend the class, they are welcome to join. All right, so today I'm going to talk about exact inference. So today and the next class, basically talk about the exact inference, variable elimination, message passing, and things like that. So these are probably the most important fundamental block of the graphical model. That's the whole reason that we use this structure way of representing the joint probability density to do inference in an efficient way. So in the first two classes, today and on Thursday, I'm going to talk about the classical approach. These are probably 15, 20 years old, and they are not at the moment frontier of the research, although you may use them without knowing them. Nevertheless, it's important to know what's going on behind the scene. Although you may not do the research exactly in this field, but it's important to know what are the difficulties, why we resort to approximation, and things like that. So let me get started with the common task when we are using probability graphical model. I think that this is something that I've already discussed in previous sessions. So I'm going to talk about two main fundamental tasks or queries in the context of graphical model. Probably one of the most common tasks are performing a query that's called inference. So it's basically, if you have a set of random variables that you connect them through your graphical model, you may ask, observing y, what is the probability distribution of x? This query or task called inference. So today I'm going to talk about how we can actually compute this quantity or this query in a computationally efficient way, given the structure of the graph and given the parameter of the graph. Another important task is learning. So you may say that, well, like so far we have only talked about the graph that like we know either the structure or given the structure we know the parameters. What if we don't know the parameters or we don't know the structures? So that falls in the category of learning. We don't talk about learning, but it's important to mention that because to do learning, you should be able to do inference. In fact, so when I'm talking about learning, I'm talking about both learning the structure of the graph and the parameter of the graph. So this is why I'm talking about, when I'm mentioning M as a model, I'm talking about both. In fact, if you are Bayesian, learning is not, so there is nothing called learning, everything is about inference. So if you are a Bayesian, you want to approach the problem from Bayesian point of view, the structure of the graph is coming from some distribution. And all you need to do, given the data, is to compute the posterior probability of n, which is your model given the data. So that model can include the parameters that you are fine-tuning or the structure of the graph that you want to infer. So if you are Bayesian, inference is like subsume the learning. If you are not learning, if you are not Bayesian, you want to approach it from more frequentist point of view, or you are a machine learner, and you're not choosing a camp between Bayesian versus frequentist, and you want to find a point estimate of like, okay, so this is the model, I want to find a parameter, give me one number. Still, you need to do inference, because usually when we construct our graphical model, there are subset of variables that are observed. The rest of those are coming from our modeling, and we have to integrate it out. To do that task, we need to do inference. So inference is a core part, is a core engine that enables us to do inference, which is the goal on its own, and learning. So what are the examples of inference? So I guess if you remember the second class that we talked about unfair casino, that there was a guy that was like flipping a coin, and one of the flipping the toss, and like one of them was unfair, and I show you a bunch of questions that you can ask. So, for example, we ask a question that, like, let's say we don't know if there is an unfair toss there, the coin there, and one thing that you want to do is to evaluate how likely a sequence of 1 to 6 are, given that both coins are plausible. So basically, you have some evidence, which is your observation of the numbers of the coin or toss, or dice, and you want to compute what is the probability distribution of this observation, or what is called evidence. So evidence doesn't have to be one variable; it can be a set of variables. It can be a subset of variables. So, for example, if you are modeling the probability distribution of x1 through xn, and only the last case are observed, so basically this is your observed, and you don't know about the rest, computing probability of that evidence or your observation entails marginalization or summing out the rest. And to compute basically this variable, we need to do inference. Another common query or question that you can ask from your model is computing the conditional probability, conditional likelihood. So let's say that I have some evidence, some observation that's coming from, so you have a model that has a joint distribution of x, e, and perhaps others, maybe y or some others. And you want to compute the probability of y given your evidence. Of course, you can write it as a base rule and the joint distribution of x and y divided by PE. So to compute this guy, remember, which was basically the same thing that I showed in the previous slide, you have to do inference. Because computing these quantity, as I will show you in the following slides, is not always easy. It's if you want to do it in a naive way, it can be very expensive. So depends. So this is also like computing the term conditional probability distribution is very general, but that's what is referred in statistics computing the posterior probability of one random variable given the evidence. So if you see that given the model and given the data, give me the posterior, that's what basically these kind of queries that we are talking about. Another important thing is that, well, x, which is the quantity that you want to estimate the posterior probability of, might not be all of the unobserved variables. It might be only a subset of random variables. So your entire model can have all kinds of. So it might have the relationship between e that you have already observed, a subset of random variables, x that you are interested to compute, and subset of variables that basically, quote unquote, you don't care. So if you want to compute the posterior probability of px given y, or x given y, e, or y given x, you have to integrate out all of those variables that you don't care about. So this basically entails computing, being able to do inference in an efficient way. Yes?
So you're saying that the variables that you're going to be marginalizing over, the point you're trying to make was that some of those might be observed and some of those you might not be.
Yeah. So you might say that, well, I have a graphical model that has a relationship between e, between x, and between z, I don't know, y, and they're all related to each other in a crazy way. And you're only interested to compute posterior probability of y given evidence. You want to remove the effect of the rest of them that you haven't observed. But what I want you to take out of this is that in all of this, whether you want to compute the posterior or you want to marginalize some of the variables out, integrate them out, you have this form of summing over, or if your variables continues integrating some subset of variables, and if you do that in the naive way, It can be very expensive. So what are the application of this? So yes.
Does this all, are we working totally in like a parametric paradigm right now?
Uh-huh.
Okay.
So right now, we are talking about the parametric case. And also we are not even mentioning the parameters. So let's say that you have a way. So when I go more forward to our model, we'll get there. But we are not even assuming that there is a parametric form, because we are assuming that like, you are given a model and you're given the parameters of the model if you're parametric. You want to compute these marginals or these queries. So as long as you can compute this conditional distribution, we are fine. If you want to do it non-parametric, you should still give me these conditionals. So it doesn't matter, I don't care how you parameterize it or how you evaluate it, because even if you're still unparametric, you have to still give me this P x given y. Doesn't matter you parameterize it or not. You just have to give me this value. But regardless of that, so this part of the course is still relevant, because if you have a lot of variables, whether you relate them in a parametric or non-parametric way, you still have to compute this integral or summation. So what are the applications of these queries? So let's say that I'm given a chain of the events. Let's say that A is the blood pressure of the person, and B is the amount of glucose in someone's blood. And if the blood pressure is high, that result in some other symptoms, which is represented B, that result in the disease C. So one of the application is, well, prediction. Let's say that if I have the amount of blood glucose, can I predict what the disease this guy may develop down the road? I don't know the intermediate random variable. It's not observed. So, but given the original cause, I want to compute the posterior probability of this. So that is the problem of prediction. So another direction is diagnosis. So you may say that, well, I know that this guy has a disease C. What can cause this? So you basically want to go the reverse direction. You want to see the high blood pressure causes disease or low blood pressure, integrating out the effect of it. So that is a problem of diagnosis. The reason I'm showing you both of this is that although the directionality of the causality here is going from A to B, the information flow can go both directions. So given A, we can infer something from C, and given C, we can infer something from A. So the information goes both directions. Also, it is important during the application of the learning, you will see that why this propagation of the information, propagation of the belief are substantial. Another important query that you are most of the time are interested in is to say that, like, well, I have a graphical model. Subset of those random variables are observed. Give me the most plausible configuration of the rest of them. This is the problem. This is very classical query. This is called most probable assignment problem, or given the evidence, you can call it like maximum over posterior. So basically, what it says is that if you have a structure of the graphical model that are connected to each other in whatever arbitrary way, and you have observed a subset of this random variables. So let's say that this is your evidence. This is what you have observed. What is the most likely? So this is, you have a joint distribution of x1, I don't know, call it E because I call it evidence. So it's like x2, x3, x4. I have a joint probability distribution of x1, x2, x3, x4, and E. And so these basically defined by my graphical model. And now you're asking me, what is, given observing your evidence, what is the most likely configuration of x1 through x4? right? So computing this value is also challenging because if you want to, let's say that these are all discrete. And so let's say that for simplicity, let's say that each of those can take 2 values. The search space that you have, if you ignore the structure of the graphical model, is the number of states to the power of whatever configuration you want to search. If you do it naively by just plugging everything into this value, into this structure, can cause a lot of computational problem for you. So one of the things that we discussed today and in the next class is that how can we compute this structure, this query, which is MPA query or maximum posterity query in a computation efficient way. So an example of that, for example, for people in the, let's say, NLP is that, well, you are given a sentence. So let's say that and this is your observation. And you have a state for each of these. So that is states represent, these are noun, verb, adverb, and so on and so forth. You want to estimate what is you want to, at the end, give one solution. What is the most likely tagging of these words? Which one is the verb? Which one is, don't give me probability. Give me which one is the most likely a verb. So that is the question of MPA. For people, for example, in a computer vision, let's say that you are given an image and you want to tag the patches in this image as is this tag belongs to a person, or these tags belong to a car, and things like that. So you have a structures, you have MRF structure. And you want the variable is that like person or the house or background or something. You want to give them a segmentation of this. So these are the example that we basically face on a daily basis. As I told you, of course, one of the application of that is classification, which I showed you a couple of those. Another example of that is explanation. So there are a lot of talk in community in the machine learning that we want to make a model that are interpretable, or we are able to explain them. And so graphical model basically gives you a very natural way to do that. Of course, the MPA query or maximum posteriori totally depends on a context. So here is an example that I'm giving you. So if I ask you a question that what is the MPA assignment for Y1, what would you answer to this? Given this let's say that it's the joint probability distribution of Y1 and Y2. What is the answer to this question? How should I approach? Let's start with, yes.
What do you mean? Shouldn't you condition it first on something to have this?
Well, this is my question. So I'm saying that give me the when I'm saying MPA of Y1, what do I mean? Yes. So basically, I want to compute max of PY1, but I'm given a joint distribution. So which basically means that I have to sum over Y2 of PY1, PY2, right? That's what it means. Right? Okay. So what is the answer to this? What should I do for this?
Sum the rows that Y1 is fixed in.
Yeah. So basically, I can say that for Y0, I have to sum these two up, which is going to give me 0.4. And for Y1, I have to give this. And what is the maximum posterior assignment for Y1? 1, right? But if I ask a different question that give me the joint distribution of y1 and y2, that should be obvious, right? What's the value for that? 0, 0, right? So the reason I'm saying is that, well, in one of them, the best assignment for y1 was 1. But when you are computing the joint, that might not be the case. So, and it is important because basically providing evidence can change your best assignments. Your best assignment are best assignment within a context. If the question that you are asking is the best marginal, that best marginal might not be the same as best joint distribution. So before going forward, this is basically reiteration of what we just said earlier in more formal ways, that for a general graphical model, for arbitrary shape graphical model, computing computing the inference, max MPA inference or marginals, in general is NP hard. So, but that doesn't mean that we cannot do that. It means that if I have a general graphical model, there is no algorithm that can solve the problem for every graphical model in a polynomial time. But there are a structure of the graphical model that we can compute in polynomial time. And most of the cases, our application fall into the categories that we can compute this, or we can approximate in the polynomial. So basically this theorem says that, well, no free lunch. There is no algorithm that solves everything. It's applicable everywhere. But if you know your structure, and if your structure falls into reasonable categories, you can do it. So, so before starting, let me talk a little bit about the general landscape of the inference in the context of PGM. Today we are going to talk about this section of the inference, which are basically exact inference. So we talk about variable elimination and message passing. As I mentioned earlier, these are not frontier of the PGM. Many of the methods that are developed in this category belongs to maybe 20 years ago or 15 years ago. Yet they are still relevant because sometimes for many of more complicated problems, some of the sub-problems can be solved efficiently with our classical approach. So these are mostly classical approach, and that you need to know before going to the research. In terms of research, most of the research nowadays focuses on approximate inference, and in general, approximate inference come into two categories, like optimization-based inference that we'll talk about it in module 4 of the class, and sampling approach. There are a lot of exciting research are being done. If you go to conferences such as NIPS or ICML, you see a lot of research going on, especially in the intersection of PGM and deep learning, when basically all of the bets are off that like we don't have any closed form solution. How can we do inference in this context? And I think that's a great area of the research. But well, before running, you have to first learn how to walk. And like today and Thursday, we try to teach you how to walk. Some of you may already know how to walk. So, all right. So the first part, I'm talking about the variable elimination, probably the most basic part of the class, and I'll teach you when it can cause trouble and how can we do it in an efficient way. Any question from the previous section of the class, the introduction that I gave? Is it clear? Move forward. All right. So let's say that you are given a chain of, so you talk to your biologist collaborator, and he has given you a complicated chain of the events of the molecules interacting with enzyme interacting with receptors, and so on and so forth. And he, at the end, said, well, I've done this study. I've done my homework in wet lab. I see this in the blood of the patient. Give me the original cause. Give me PA. I mean, of course, I'm not, for sake of example, in this class, I'm not going to show you a gory graphical model. So let's say that this is very simple. It's just a chain. A causes B, B causes C, and so on and so forth, till you get your E, which is your evidence, whatever you observe. I'm interested in computing. I may ask, like, how likely this event is. Is it a rare thing, or this is something common? And give me the probability. One of my queries can be computing this PE. So what should I do for this PE? You have a graphical model. Let's say the parameters are, you know the parameters. Yes.
So you're given the CPDs for each of those.
Yeah, everything is given.
So would you start at A and just go through the chain?
Yes. Sum them up, right? So PE is summing up over D, C, E, and E. Well, even for a simple case, assuming that each of those have K state, discrete case, this summation can have how many terms? Let's say each of those have K state. How many terms we are going to get? K to the power of 4, right? And you can see that this is a tiny graphical model. It's actually a very simple one. Even for this, I have a lot of terms like to compute. And as soon as it becomes complicated, then the summation, yes.
We can be a little smart and we can eliminate one variable.
Yes. So we are going to try to become smarter in the following slide. But that's a good idea. So let's just start with that. That's a good idea. This is my joint probability distribution, and this is basically showing the factorization of that. So what do you suggest to do?
We first eliminate A.
First, eliminate A. Okay, so why should I first start with eliminating A? Because you can do that in any order, right? If I do that with A, do I make things simpler? Because if I compute A, this is a term that I have. It's fine. It's not a bad idea. But I'm saying that why didn't you start with C?
A doesn't have any conditions.
Okay. Yeah. So the intuition is that I can get rid of A because this is the only term that has A. But if I would have started with C, this C depends on a B, so I can still get rid of this term. Right? Could you also start with maybe E? E is observed, right? What does it mean to start from E? Huh? You can sum over. You can also sum over D. Yes, you can sum over D. So, well, by the way, like, there is nothing to stop you from starting from E because like E is observed, and it's basically probability of. So let's say that E is a capital E, and we have observed E is equal to small e. So it's one of the specific configuration of E, right? So when you are saying that start from E, you can say that, well, E has different states. Let's say that, let me call this E1. So E1 through EK, and one of them is observed. If I start from there, it means that the probability of that is 1, the rest of them is 0. It's like a very stupid summation. But yes, we can start from A, we can start from D or E. E is a little bit degenerate. But let's choose one. Let's go with your recommendation. So let's start from A. So what I'm doing is that I'm pushing the summation forward. So I push E to forward. So all of the terms that depends on E produce one term. And so what is the resulting term? You get rid of A. What is the resulting term? This is just a term which is what? Huh? louder.
P of B.
B. Okay, so it's basically a term that only depends on B because you got rid of A, right? So you have some terms that depends on B. What should I do next? Yeah. So basically, you are saying that collect all of the terms that are related to B. This is a term that's related to B. Push all of the terms that are related to B. Push the sum forward and get rid of it. So that's what I'm going to do next. We got rid of A. So I can bring this guy closer and get rid of B. Right? Exactly the same thing that you mentioned. So hopefully by now you see that there's a procedure. I started from a tail of this chain. I pushed my the sum forward, and all of the terms that are dependent on that variable, I start summing that up. Right? I can do that for C, for D, and so on and so forth. Now, oops. So what is the computational complexity now? Every time you compute a K, right? What is this summation entails? What does this summation mean? Let's say that we are talking about discrete random variables. We are given a CPDs. What does it mean to compute this summation? So let's just start with CPD. What is the form of CPDs for discrete random variables? Yes, it's a table. Or I can say it's a matrix.
Is it a matrix multiplication?
It's exactly. Yeah, it's a matrix. It's a matrix what multiplication? Complication matrix with what?
With the prior.
Right, which is a vector. Right? It's a matrix vector multiplication. Right? We started with A. So A is only dependent on itself. So it has a probability distribution of different states of A. So I can write that as a vector, right? I can write this as a vector called, let's say, V, which is, I don't know, k-dimensional. And I'm writing as a delta k because it sums to 1, so it belongs to so-called sequence. So, right? Okay. And then I have a CPD, which is a vector. Right? And I'm multiplying that with this. Is that part clear? I'll get back. Is that part clear? What is the computational complexity of this matrix vector multiplication? Come on, guys, computer scientists. So, what is this matrix vector multiplication? I have the dimensionality of delta, or your message of PA was k. This is k by k. How many computation? What is the complexity? K squared, right? For each of k, I have to do for loop and repeat it again. So it's OK squared. And I have to repeat it for n variables. So what is the total computational complexity? Right? Remember what it was before? Oh, what it was before? K to the n. So it's quite a bit of saving, right? So, sorry. What do you ask question? Done. Okay. Okay. So, but hopefully you see that the reason that we can do this is exactly what you said on the back of the class, that it's a matrix vector multiplication. And the associativity of this operation allows you to push this. So you have A, let's say that M of A, which is CPD of the first one, M of the B, M of the C, M of the D, and so on and so forth. I can do this multiplication however I want, right? I can first compute this multiplication, and then this, or I can start with this. The reason that you can push this sum forward is because of this associativity. To see that example, let's say start with what we call annoying fly. So let's say that you have 3 rooms, and there is one smelly cheese in one of the rooms, right? And there's a fly that just does things randomly, but it can jump from room 1 to room 2, or room 2 from room 3. It cannot go from 1 to 3 or 3 to 1, but it's just like the state that it goes, right? Now, at every time, we are basically observing where this fly is. I mean, of course, because of the smelly cheese, it wants to be in the room 1, but it's random. So it just jumps from the room, but it just happens to be in the room 1 more often. So now, so let's say that I'm going to represent the CPD of this distribution. So let's say that for now, let's assume that I want to compute the state of this fly at the time t. Right? So I can represent this as a chain, right? Where the fly was at the time 1, and then where the fly was at the time 2, and so on and so forth. By the way, what is the values of these random variables? x1 to xt. Huh? 1 to 3, exactly. So the state of the room, like which room it is. So the CPD of that, as I told you earlier, can be represented by a matrix, right? So the probability that the fly is at the room I, given that it was at the room J before, is this CPD. So the columns of that sums to 1. By the way, what would be the probability distribution of, let's say that, let's play with the example. Let's say that we want to compute the probability distribution of this fly at the time 5. So this chain is t is equal to 5. So if I know this, let me call this, oh, well, I've already called this M. So let's call this the M matrix. And let's say that the status of the P x1 was V. How can I write this in a matrix format? Help me write in the matrix format. At the time 1, the probability distribution of this was V, which is a V vector, right? It's a vector that it is, how many dimensions? 3, right? And M is the CPD of going from room I to room J. If I have I'm summing up over these 3 states, how can I write in the matrix vector form? Let's start with 2, right? Probability distribution of Px2 given x1. Huh? MV, exactly. So the second state would be
M squared.
yeah. So the 3 state is going to be, right? So now I ask you, well, for T state, it's going to be MTV. Can you compute where this fly would be in the steady state or in infinity? How can I do that? So let's say I want to send T infinity.
Compute the eigenvalues.
Why?
Because if you do eigenvalue decomposition, then we have P sigma P and powering them M equals P.
Yeah. So it's basically you are saying that at the infinity, this is like the probability of that is stabilized. So it doesn't matter that I hit it again with. So this is basically the probability of that as the infinite at the time infinity, right? And this problem is when I write something for you in the form of MPP, you should see that this is the eigenvalue decomposition problem. And what is the eigenvalue of this? So basically all I need to do is that compute SVD on this. And what's the eigenvalue that I have to find? 1. Right? Because for the general one is MV lambda v, and this is for the case that lambda is equal to 1. So if I compute for a chain, if I compute the eigenvalues, eigenvalue decomposition, and choose the eigenvalues that's corresponding to 1, it shows me the steady state of this chain. So it should come. So one question. So if I do SVD, I'll get that. If I do SVD, why this P should be? I mean, SVD doesn't tell us that the values are positive or negative. But here is a probability. So it means that the V's sum up to not only is non-negative, but sums to 1. So if you have a CPD, if you have a Markov matrix, if you compute singular value composition, the eigenvalues corresponding to 1 is a normalized probability distribution. Yes?
I was going to ask, so you're assuming that there's like a translation invariance, like the
What do you mean translation?
CPD doesn't depend on time?
Yes, yeah. I'm assuming that doesn't change with time. Okay, so going back to the idea of a message passing in a chain, so it seems that when you are computing, you remember you push the summation forward and compute something and plug that in, compute something, plug that in, plug that in. You see that there is some sort of like a message passes. And this basically, a great example of that is in the, David McKay's book, who I guess passed away last year. It's a very great book. And he has very nice example representation of that. So let's say that you have a chain of soldiers that only see the soldiers in front of them or soldiers behind them. And they all want to know how many soldiers are in the row. So what is the right way? How can they find out how many soldiers are in this row? I can only see the soldier in front of me, soldiers behind me. Is there any way that we can talk to each other, only this guy, so that I can find out how many soldiers are in this line? How can I do that?
You count off.
Huh?
You count off.
Count off?
Yeah.
What does it mean?
So like the first guy says 1, and then the next guy says the current number you heard before plus 1.
Okay, so you are planning some sort of like passing a message between them. And this is basically what we do. So the first soldier say, I'm 1 behind you. The next one, okay, 1 behind me. So the next message I have to send to the next one should be 2 behind me, and so on and so forth. So when you reach to the person in the middle said that there's 1 of me, and I got a message from the guy behind me that says 3 person behind me, I'm going to send a message to the next one, the 3, and so on and so forth. Then when the message reached to the end, he has to send a message back. So he got the message from everybody and says that, okay, so now I'm 1 before you. And compute it all the way to the same person and say that, okay, so there is 2 persons before me. Because all you know, that so far you have received a message from the back, so you don't know how many people are in front of it, right? So they have to send a message to know how many people are in the front. So he got a message that there are 2 people, 2 soldiers before me, and he already knows that there are 3 people behind him, and there is only 1 of him. So the belief that he has is that 2 plus 3 plus 1 is 6. And the same with all of them. So with the 1 round of message passing forward and 1 round of message passing backward, everybody knows at the end when this the message passing finishes that how many soldiers are in the row. And this is basically the general idea of the message passing that we'll go through more detail in the next class. So, okay. Yes.
Is it the minimum number of the queries that can? Like,
What does it mean, minimum number of
well,
queries?
everybody can tell the person in front or back.
So, well, if you stop this somewhere at the middle, you don't know how many left behind. So so basically, this message should reach all of the nodes in the graph or all of the soldiers. You cannot stop anywhere, right? Make sense? So, well, of course, it's a very contrived example. It's a very simple example that things are for basically a chain. What if we have a general graphical model? What about the general DAG? How can we extend this idea for the general DAG? So, I mean, conceptually, it should be that difficult. So let's say that these soldiers are structured in some sort of like a three-way, so then they're connected through branches. And they all send a message. And this message, so for example, this branch of the tree can send a message to this guy that there are 3 here. And this branch of the tree can say that there are 7 people. And this branch can say there are 3. And finally, say that there are 3 here in this side of the branch. There are 7 in this side of the branch. There are 1 of me. Total, there must be 11 here. So conceptually, it makes sense. So it's just a matter of instead of sending a message over the a chain, we have to send it through different branches. So, however, this is the case. Oops. The problem happens when there is a cycle. And cycle is very common for a graphical model. Remember, although we are talking about DAG, then you're removing the arrows. I told you, this is basically a flow of information. It's a flow of information that goes through different nodes in the graph. So it doesn't matter that your graphical model is where the arrow is pointed out. When you are talking about the flow of information, the arrows are all removed. Basically, to put it in more rigorous way, our graph is moralized. So chains are unavoidable. So how can we do this message passing when there is a cycle in this graph? So in the following slide, we're going to talk about basically that. So is there any questions so far? Nope? Clear? Is it clear why cycle can cause trouble? Because the cycle can cause trouble because it depends where this message reached to this guy, right? You have to send these messages in a scheduling, in a specific scheduling network. So let's say that before the message sends to this guy, so you send a message, and the message from this guy hasn't arrived yet. And this guy said that, okay, so there are 1, 2, 3, 4, 5, and one of me, well, just like 5 plus 1, 7, right? And it has to wait until the message from the other one reaches, and then say, oh, okay, it's not 5. Let me send another message. And it may never converge, right? So you may receive the message in non-synchronous way. So in a tree, it's very obvious. In a chain, is very obvious because you send a message, there's no loop, the message come back. In the tree is also very obvious. You start from the root, you send to leaves, and leaves send it back. But if there is a cycle, the message can get stuck in a cycle. And you may not, so there is no proof of the convergence there. That's basically on a very high level. We'll go to the more detail in the following slides. Okay, so let's start with more complicated graph. Let's say that it's a food chain. And the variable represents who eats whom and basically that. Well, you can assume any other scenario, but basically we have to motivate you with a little bit crazier graphical model. So let's say this is a graphical model, and you have evidence at the variable h. And you want to compute the probability of PA given h. By the way, I showed a bunch of queries. What kind of queries is this one? H is observed, rest are not observed, and I want to compute PA given h. What did I call this query before? Huh? Not diagnosis. Diagnosis was, well, it's diagnosis is usually mostly for chain, but in general, the conditional probability is basically computing the posterior probability of PA given h. Posterior belief, right? marginalizing out rest of the guy here, right? Okay. So basically what I need to do is that, of course, given the graphical model, the joint probability distribution of that is factorization that's coming from graphical model. So the factorization of this graphical model is PA, D given A, F given A, E given D, and so on and so forth. The factorization, I can write the factorization as you see on the top. Now, I want to compute this posterior, which means that I have to get rid of the rest of them. So I have to sum over the rest of them. So I'm going to pick an ordering between. I just say that this is my ordering. I can take any other ordering, but let's start with this. And we'll see the effect of this ordering later on. But let's start with this ordering. Is the setting clear? What we want to do? Okay. So we want to basically compute the PA given H. So it means that we have to get rid of the rest of the variables that are unobserved, or we don't care about them. And the factorization is coming from my graphical model. So the first step is that, as I told you, the evidence, so whenever you're observing an evidence, you can basically view it as a delta function. That I've seen this evidence, now to change my CPD, that the probability of these things that I've observed is 1, the rest of it is 0, because I've already observed that. So you can view this as, you can view that like H is also part of the chain. There's nothing different between whatever you have observed or what you are integrating out, because you can manipulate CPD, you will still have this matrix vector format. So, so I'm just saying this just to make the notation easier, because although I'm conditioning on H, and you may say that, oh, H is a special, but if I define a CPD as a delta function, it's just, there is nothing special about it. So, so it's basically a delta function that, like, I've observed H tilde as the actual manifestation of the H that I see. I don't see the rest of it, so it's like you can view it as if H has a K state, and this is the H prime that you see. This delta function is 1 here and 0 everywhere else, right? Okay. So so now I have to sum over this guy with the specific ordering that I've been represented here. So I'm going to start with H first, because that's my observation. So I can push this forward. This term is the only term that depends on H, and I can integrate it out. And of course, this is because H is observed is a delta function, is just basically equivalent of what? Like reading one row of the CPD. Okay, so that basically remove this term and produce a message that I'm going to represent it with MH E of F. The reason that I'm representing as MH E of F is that this is the notation I'm going to choose. Every time that I have a message that's result of eliminating one random variable, oops. Okay, good. So I'm going to show the random variable that I'm removing here, and the rest of the variables that are eliminated, or this message is dependent on it, is going to be inside of the argument. Is that notation clear? Right? So if I'm removing some random variable in the middle, let's say call it t, it's going to be mt, and the argument is going to be whatever left hasn't been integrated out. Okay, so that's a notation. All right. So in this factorial form, I just push the H forward. I push the H forward, and that was the only term that depends on H. So the thing is that you know that in this term, I remove H, but I have introduced a term that has an argument of F and E. So in my graphical model, E and F become dependent. I can't simply remove this and then let these arrows hang in the air, right? I have introduced a term that makes them dependent. Is that part clear? Is that clear?
So you moralize them?
You could have started, that's a good term to use, but like we are something a little bit beyond that. So that's a good term. So let's start with moralization of this graph. If I would have started with moralization of the graph, what arrows what are the procedure for moralization? So this, let's say that I've given that guy in the top, and I wanted to moralize this. What should I have done? Connect this guy to this guy, and what else? Anything else? No, I think we're good, right? That was moralization. Yes, but as you see that in the following, as I'm moving the other terms, you see that I'm doing something other than moralization. But that's a good insight. So I got rid of H, which resulted in dependence of E and D because I've introduced a term that make them dependent. I'm introducing a factor that makes E and F dependent. So let's remove the next one. So I want to remove G, right? I want to eliminate G. So yes.
I don't understand why you call them dependent now. Maybe MH factorizes.
Huh? But you have a term. What does it mean that it's factorized?
Well, MH of E and F is equal to, I don't know, the N of E times.
But that doesn't matter. You're not really talking about the directed graph problem. You remove all of the arrows. You're trying to push the information back, right? So now we're talking about the undirected graph problem. We have a term that has both E and F. Doesn't matter what is going on inside of it, but it doesn't have the meaning of it doesn't have the probabilistic meaning anymore. It just means that there's a term that connects them together.
Dependent just means that they are coming together.
Do you remember the definition of the UGM? That the UGM, the factors that we had, was just said that is affinity between them. We can interpret them as marginals. We can interpret them as joint distribution. We can interpret them as CPD. Remember that? It just means that there's a term that has both of them at the same time. I integrated H out, and I produce a message that in the argument has both E and F. So I basically introduce a factor that connects them together. Make sense? Okay, so now I want to eliminate G. What should I do? You have a term that's coming from your previous message, and you want to eliminate G. What should I do? We just talked about it.
Push the sum forward.
Push the sum forward.
So just P of G dependent on E.
So basically, push the sum forward, find all of the terms that depend on G, put them all together, so it's going to be only this term, right? Is there any other term? Nope. And if I sum that up, I sum over G, this is CPD, so it sums to 1, right? So that goes away completely. So I can get rid of this and get rid of the arrows because the only thing that's dependent on it is E, and E is still there. And I'm not introducing any extra relevance with anyone, any dependence with anybody else, right? The G is removed, and there's no G here, and there is no term that's dependent on G, so I don't need to introduce any extra H. Okay, so I got rid of G. This is my new undirected model. Let's eliminate F. Now you guys do, yes?
Why is the last term dependent on G, but the probability of E given C of D not dependent on G?
Why? What's the probability of what?
We were saying that this like marginalized out H, which is like a function of E and F, is dependent on G because of E. And then we have the probability of E given C of D also. Why is that not also dependent on G?
Well, do you see any other term there that is dependent on that?
It just seems like we're saying E is dependent on G, so we need to keep this one E in, but this other G is.
Well, you integrated, when you're saying that you're eliminating it, right? You're eliminating that out. So all of the terms that has a G in it are gone. It produces something that, you can view it as a function, right? It's a function that has G in it and E in it at the end of the day. That's what it is. You sum over all of the G's, so there is no G in it, right? So unless there is somebody else that has a G, and let's say if I had some other arrows that goes from here to here, right? What would have had the factors? In the factors I would have had G given B and E, right? That's my new graphical model. You see that? If I eliminate this guy, then I should have connected B and E together directly. Does it make sense? I'll get back to you. Sorry.
I think that what he was, maybe this is what you were referring to, that when you were doing the integration over the elimination for G, it looked like you were also had in the integral M of H dependent on E and F. That factor that we introduced in the previous elimination,
Right.
It looked like that was also dependent on G for some reason. But I don't think that was what you intended. You drew a box around P of G given E and M of H.
So this one, so here.
So when you wanted to do the elimination over G,
Uh-huh.
you push forward the term that had G and dependent on E.
Yes.
And then, but you drew a box around that and the term that we got from the last elimination, M of H, E, F.
Right.
So that term didn't have any G in it.
Well,
That M, H, E, F didn't have G.
so let me explain it this way. So when you are eliminating H, so let's say that H is unobserved for a second for simplicity, right? We have a bunch of terms that, like, because of the structure of the graphical model, we had terms like here we have H, given E and F, right? So at the end of the day, it's just a function. Forget about that it's normalized, it has a meaning. It's just a function that has F of H, E, and F. That's all, right? When you are summing over all of the terms, you introduce, so if I sum over any of these terms, so let's say I sum over F, there is no F after that, right? F is gone. So the output function becomes something that has H in it and E in it. And if they are not if they are not connected in the graph, you have to connect them, because when you're eliminating them, you have to account for the things that are introduced. So the difference here is that when I was eliminating, when I'm eliminating G is only dependent on E, right? So the only term that I have is a form of G, E, right? So if I'm summing over G, the new resulting term is only a function of E, and it doesn't introduce E with somebody else. So this is just viewed as a placeholder that introduced that it is for our bookkeeping. So this graph that I'm introducing is not a probabilistic graph. It's just a dependence graph. So it's like it says that which terms are dependent on what other things. Did I answer your question?
Maybe, I'm still confused, we can talk.
Okay, sure. All right, so which direction I'm going? Now let's say that I'm removing F. So if I remove F, what should I do with the same logic? I have to bring the sum inside, get rid of all of the term that has function of F. But I have to do something else with the graph. What should I do with the graph? I push the terms that has F in it, which is this term and this term. What should I do after that? I have to do something to the graph.
Join F and A.
Join F and A. Well, you're removing F,
Oh, sorry, E and A.
right? Why you don't? The reason that you don't connect A and D because it's already connected, right? So, and this is exactly what we do: is that we push this forward, we produce a new block of dependence, and we connect this together. This graph is, as I said, it doesn't have a probabilistic meaning. It just means that there is a new factor introduced. It's not normalized. Don't just interpret it as a function of dependence. And I can continue doing that. So next step, I'm going to remove E. Again, push the sum forward. Clump all of the terms that has E in it. So what should I do after this? If I remove E, what should I do? So I'm going to get the new term that E isn't removing it, but that still has C, D, and A. What should I do? Connect CD and AC. Yes, exactly. Because the new term has a factor that has M. There is no E in it, so there has an A, has a C, has a D. So I have to connect them all together. And that's what I'm going to do. Yes?
Does the value of the vector important?
Louder.
Does the value of the vector important?
Does the value of the vector important? Well, the value of the vector is coming from your summation, right? So it's basically you can view this message is a vector if we're talking about a discrete random variable. So you can view this as a vector that's coming past to the next one. So every time that you do this summation is as if you were doing matrix vector multiplication, right? The message comes as a vector. You multiply with CPD to compute that sum, creates a new vector. Does it make sense? So the value of the vector is important.
So you already recall all the value, right?
Huh? Yes.
Okay.
Yeah, exactly. So to compute all of that, you have to do this sum, which is for each value, compute. So it's like you can view the matrix vector multiplication as just a bunch of inner product, right? That's what you do.
So it does not only represent a kind of relationship, but the value is also very important, right?
Yeah. The value, yes, the value is important. It's basically a belief that's coming from that. This is the message that I got. It's not finalized because I haven't finished passing the messages, but it's basically I'm just collecting information from the rest of it. And the next is that if I eliminate D, again push the sum forward, sum over all of the terms which has D in it. What should I do after that? So all of the terms that has a D in it is this guy, right? So I brought the sum inside, and I have this term that has only A and C. Do I need to do anything with this graph? No, because the new term that is introduced has A and C in it, and A and C are already connected. So I just have to get rid of D without worrying about the rest of it. Yes?
Drawing the graph, what are you using that? I'm not following that.
So this graph is basically, if I don't have this graph, you don't know how to, what is the term that you have to compute. So I'm using this graph. If you think about it, that you want to implement it mechanically, right? Okay. If you want to do it mechanically, you have the original factorization is basically multiplication of a bunch of factors. You want to know which factors you have to combine together to do that matrix vector product, right? These graphs will tell you that this guy and this guy and this guy have introduced a new connection, and these are all of the values that has to be introduced. So go check their factors. You can view a graphical model, as I said, it's like a data structure. There's a bunch of factors, and the graphical said that, well, at the end, the probability is these factors multiply. Whenever you're introducing a new edge, you are basically saying, okay, go and retrieve that factors for me, because I see the connection. So And finally, we finish with this. But you can see that if each of those has k random variables, the naive way of computing that would be 1, 2, 3, 4, 5, 6, k to the 6, while this one's going to be k squared, k squared, k squared, k squared, k squared, k squared, k squared is going to be basically k squared with just, I don't know, 6k squared.
Why is
Sorry, squared.
why would it be k squared?
Because the matrix vector product.
It's not always a matrix. It can be a tensor.
Yes, that's a good question. Yes, that can be a question. That can be a problem. So do people see why it's not always matrix vector product? So, Sometimes you have two parents. So if you have one graphical model that goes like this, the CPD of this is a vector. But if you have two parents, the CPD of that would be a tensor. Right? So that means that my summation is not going to be k squared. It's going to be what exactly? Yeah, it depends on how big that tensor is, because it can be 3-dimensional, it can be more dimensional, right? So the cost that I'm paying depends on every time that you produce this extra link, how big that click can become. If you start connecting them together, and in one of them, so I guess in one of them, you saw that almost everybody was connecting to everybody. This is crazy. It's like everybody is connected. So your conditional click is pretty big. So, and that depends on the ordering that I chose. Nobody asked me question that like, why did you start with B, C? So why did you start with this ordering? You could have done any other ordering. Now the thing is that depends on the ordering that you choose. The computational complexity of that will change, because you introduce only the cases that have only one parent, so only have matrix vector product, or you may, at some point in your graph, you can introduce a huge graph that everybody's connected to everybody, and you're in trouble. All right, so am I going forward or backwards? Yes?
Can the value of the messages at each of the random variables be treated as the expected value of that random variable under the CPD for that variable?
Can this be computed as a, it's computing an expectation, but that's not the expectation of that random variable. Because expectation of that random variable, so it's like, if I want to compute P expectation variable of B, it means what? Like, it means that I have to sample B from PB, right? But that's not what I'm computing, right? It has a form of expectations. It's expectation of something, but it's not expectation of that random variable. Yes. So it's basically that was the procedure that I started. I started with the directed graphical model. During the process, I ended up moralizing the graph, and I start eliminating and get different graphs. So as one of you guys mentioned, this is the general procedure. We'll go over that next time with more rigor, because we want to basically make it mechanical, because we want to write an algorithm that if I give you a graphical model with the CPD, you should be able to compute an arbitrary inference. But right now, we just gave you an intuitive sense of how this works. Yes?
So does it seem to be simpler to do this operation using factor graphs? I mean, to visualize it?
Would it be easier to do simple? So we will talk about that in the next session on how to do that in a factor graph. But what do you mean the simpler? What does it mean simpler?
Maintaining the factors like here.
That's basically what we are doing. Yes, exactly. If you want to do that quote unquote mechanical way, which basically means like computer write an algorithm to do this, yes, we have to resort to factor graph. Yes, that's a correct intuition. So basically, the general procedure is that We are given a DAG. We convert it to the graph, to the undirected model, just remove the arrows, moralize it, and do this elimination. That during the course of this elimination, we introduce new connection because of the message passed. And in the next session, in the next class, I'm gonna be more formal about it. Like today was only like an intuition, to get an idea, to give you an idea of what we are doing. But in the next class, we will do that in more formal way. But to get a little bit closer to the formality, this is basically what we did. We started doing this process. That we started removing H, and then G, and so on and so forth. So, but like every time that we remove a random variable, we had a set of a term. So it's like a clique, or a set of factors that are all dependent on each other. And we compute this summation over this set of factors. And every time we did this, we introduced new arrow, or sorry, like a new edge between random variables that basically tells us how to combine these factors. I agree with you that it's much better to do it in the factor graph, and we'll do that next class in a factor graph, but it's just to get an intuition that why we are introducing these new edges, because these terms that combine them together is as if they're drawing new connections. And that's basically give us a heads up which factors has to be included in the computation. So, so basically we started with H, introduced new message, passed the message, and reshape the graph, introduce new edges, and then like basically the graph that I'm showing you here are all of these new factors that are introduced due to the nature of the message passing. So you can view that we started from this term, which entails these factors, and then we went to these, removing G, which introduced the terms that has G and H. Next, we introduce, I guess, F, that entails a term that has F, E, and A. And then in the 4, I got rid of, I guess, D, that has the terms and so on and so forth. And basically, you can view this as a message that passed between, not between nodes, but between a subset of the nodes. So, and this is basically the message that I want you to take out of this, is that it's a message that are not passed between a node. It's a message that are passed between a subset of the nodes. And the variable elimination and extra edges that I introduced was because I wanted to see what are the subset of the nodes are within each of the stage of this message passing. Is that clear? So that is called click tree. Next time we're going to go over how to build this click tree in more formal way and more basically mechanical way. But basically what I want you guys to do is that I want you guys to read the chapters before that, because these two chapters are a little bit abstract, and because there are lots of bookkeeping, they're a little bit hard to keep track of. But please read the chapters before coming. As a general idea, as I told you, there was no free lunch. So for a general graph, the problem is NP hard. And the fact that we did variable elimination doesn't change the nature of the problem. So there should be something that I'm hiding from you. And it's basically that this new graph that I introduced in the middle are basically what I'm hiding. I think one of you guys mentioned that it's not always matrix vector product. It can be tensor product. And every time that I'm introducing this graph, the size of this graph can grow and grow and grow. So for the general graph, when I'm introducing these new edges, the size of this tensor may explode, which basically bad in terms of memory consumption and computation. So to give you an idea about computational complexity, every time we do this either matrix vector product or tensor vector product and so on and so forth, the cost that I'm paying, the maximum cost that I'm paying is the size of the biggest click. So if during this process, my size basically is exponential with respect to the size of the click. Because remember, if the size of the click was 2-dimensional, it was k2. If the size of the click is 3-dimensional, it's k3. So if I'm during the process, I introduce a click which has m variables, going to be km. So I'm back to the level 1 that I have to pay exponential, and that's because the problem in general is empty hard. And so basically, the cost that you are paying is basically the size of the biggest click that you have. So the idea here is that you have to find the ordering that the biggest click is not too big. And because it's an NP-hard problem, there is no way to avoid it but having a good heuristic or having a graph which is quote-unquote tractable. So to give you an example, let's say that I have a star. If I start with removing this node, I'm not going to introduce any extra edges. I can keep removing this in the periphery and not introducing new edges because all of the factors are pairwise factors. But if I do some silly way of eliminating factors and the star said, like, I feel brave, I want to remove the one in the middle. So what would happen? You create a complete graph, which means that everybody is connected to everybody after I remove this guy. And the cost of that is, in this case, going to be K4. So the ordering of elimination is important. And we're going to talk about that later. Talk about this. So to summarize, I gave you an intuition of message passing and basically variable elimination, that they're all related to each other. So this summation or matrix vector product or tensor vector product that I do is basically the message that I compute that goes from click to click. You can view this as, so if your graph is very simple, it's basically as a chain, you can view it as a message that passes from variable to variable. But that does not work when you have a loop in your graph. And if you have a looping graph, you have to view the message passing as a message that passed through a click of the variables. And in the next class, we're going to talk about how to build this click and how to pass messages. Okay, that's this.